Somewhere in the darkness between galaxies, a photograph was taken, and when scientists looked at what it showed, some of them went quiet in a way that had nothing to do with awe. The James Webb Space Telescope was built to confirm what we already believed, to see further back in time than ever before, and find the universe behaving exactly as our most successful models predicted. Instead, it found galaxies that had no right to exist. Massive, structured, fully formed objects burning in a cosmos that was, according to everything we understood, far too young to have made them. Not slightly off, not within the margin of error. Impossible. And that was just the beginning. Because Webb's images did not arrive in isolation. They arrived at the exact moment cosmology was already fracturing from the inside. The rate at which the universe expands cannot be measured consistently. Two methods, both precise, both trusted, give answers that refuse to agree, and the gap between them is not closing. A Nobel laureate stared at this data and said 4 words that have haunted physics ever since: not as metaphor, not as speculation, as a conclusion drawn from the numbers themselves. The model we built to describe reality, the framework that explained the Big Bang, the formation of stars and galaxies, the geometry of space itself, may not be describing our universe at all. It may be describing a universe, a local approximation we extended to the edge of everything and then watched break apart when the evidence caught up. What you are about to encounter is not a story of discovery, it is a story of unraveling, of data that does not comfort, constants that will not hold, and a silence at the origin of everything that no equation has ever broken. It begins with a photograph and thousands of galaxies that should not exist. There is a moment in science, rare, unsettling, and oddly beautiful, when the instruments we build to confirm what we already believe instead return something that shouldn't be there. Something that sits quietly in the data, refusing to move, refusing to be explained away, until finally the people looking at it have no choice but to say the words out loud: we were wrong, not slightly wrong, not wrong in the margins, wrong in the foundations. July 2022 was supposed to be a celebration. The James Webb Space Telescope had cost $10 billion and roughly 30 years of human effort to build, launch, and deploy. It had survived a journey to a gravitational parking point nearly 1 million miles from Earth, unfolded its golden mirror segments in the cold dark of space like an origami flower made of beryllium and ambition, and finally, after decades of delays and setbacks and held breath, it opened its eye and looked at the universe. When NASA released the first deep field image at a White House briefing on July 11, 2022, the reaction was what you might expect: gasps, awe, a standing ovation. President Biden called it a historic day. The image showed thousands of galaxies spanning billions of light years, bending around each other through gravitational lensing, shimmering in infrared light that Webb could detect with a sensitivity no instrument before it had ever achieved. It was, by any measure, one of the most extraordinary photographs in human history. But within days, something else began to happen, something quieter and considerably more disturbing. Astronomers around the world started downloading the actual data, not the pretty picture released for public consumption, but the raw scientific information embedded in those ancient photons. They began running analyses, cross-checking redshifts, estimating stellar masses, calculating the ages of what they were seeing. And then, one by one, they started sending each other messages with a tone that was less wonder and more alarm. Because buried in that first sweep of deep sky observation were objects that, according to everything humanity understood about how the universe works, simply should not exist. To understand why those objects caused such a crisis, You need to understand what astronomers expected to find, and more importantly, why they expected it. The prevailing model of the cosmos is called Lambda CDM. That name is a combination of two things: lambda, which represents the cosmological constant, a term describing the energy of empty space that drives the universe's accelerating expansion, and CDM, which stands for cold dark matter, the invisible gravitational scaffolding believed to give structure to everything we can see. Together, these two components form the backbone of what cosmologists call the standard model of cosmology. It is extraordinarily successful. It correctly predicts the large-scale structure of the universe, the way galaxy filaments and voids are distributed across billions of light years. It correctly describes the temperature fluctuations in the cosmic microwave background radiation, the faint afterglow of the Big Bang itself. It has passed test after test after test for decades. Most cosmologists regard it not merely as a theory, but as a framework so thoroughly validated that working outside it feels professionally risky. One of Lambda CDM's central predictions concerns how galaxies form, and it is very specific about timing. The model tells us that in the very early universe, shortly after the Big Bang, matter was distributed almost perfectly uniformly. There were tiny fluctuations, ripples in the density of the primordial soup, but these were small. Gravity went to work on them slowly, patiently, pulling slightly denser regions together over vast stretches of time. First, small clumps of dark matter formed what cosmologists call halos. Then ordinary matter fell into those halos, cooled, and collapsed further to form the first stars. Those stars burned bright and hot and died, seeding the surrounding gas with heavier elements. Over time, small protogalaxies formed. Then, those small protogalaxies merged with others. Then those merged with more, building, always building, slowly assembling larger and larger structures from smaller pieces in a process called hierarchical structure formation. This is not a vague or qualitative prediction. It has precise mathematical consequences. It tells you with reasonable confidence how massive a galaxy can be at a given point in cosmic history. And the key point, the point that makes what Webb found so explosive, is this. In the first few 100 million years after the Big Bang, the universe simply has not had enough time to build anything large. By the time you reach what cosmologists call a redshift of about 10 or higher, meaning you are looking at light emitted when the universe was only 300 to 500 million years old, Lambda CDM predicts that galaxy formation is in its infancy. You might see small, irregular, chaotic protogalactic fragments, diffuse clouds of gas in the early stages of gravitational collapse, the first tentative hints of what will eventually become galaxies billions of years from now. What you are absolutely not supposed to see are mature, massive, structurally complex galaxies. Not yet. The universe hasn't had the time. And then Webb looked, and that is exactly what it found. The catalogue of anomalies began accumulating almost immediately. Among the most studied examples is the galaxy designated JADES GSZ 13-0, observed at a redshift of 13.2, meaning we are seeing it as it existed just 320 million years after the Big Bang. This is an almost incomprehensibly early moment in cosmic history. The entire age of the universe is roughly 13.8 billion years. 320 million years into that span is the equivalent of looking at a full-grown adult and learning they were somehow fully mature at the age of 2. And JADES GSZ 13-0, while not enormous by modern galactic standards, exists at an epoch when nothing that's structured should be there at all. It is not a diffuse protogalactic blob. It is a galaxy. A real, formed, light-emitting galaxy, standing in a period of cosmic history that was supposed to be empty of such things. But JADE's GSZ 13-0 was only the beginning. In early 2023, a team led by astronomer Eva Lebey published a paper in the journal Nature that escalated the situation from surprising to genuinely alarming. Lebey and his colleagues had identified a collection of galaxy candidates in the Webb data sitting at very high redshifts, in the range of 7 to 10, meaning the universe was somewhere between 500 million and 700 million years old when the light we're now detecting left them. These weren't just slightly more massive than expected. They weren't modestly ahead of schedule on the cosmic calendar. The stellar masses that Lebey's team calculated for some of these objects were staggering, in some cases estimated to be comparable to our own Milky Way, which spent the better part of 13 billion years assembling itself. The team noted that some of these candidates appeared to contain stellar masses roughly 100 times greater than what the Lambda CDM model predicts should be possible at those epochs. 100 times greater, not 10% off. Not twice what was expected, 100 times. The phrase that entered the scientific lexicon almost immediately was universe breakers. It was not a term coined by journalists looking for a dramatic headline, though journalists certainly used it enthusiastically. It came from the scientists themselves, from people who had spent careers operating within the Lambda CDM framework and who recognized immediately that what they were looking at was not a small discrepancy to be smoothed over with an adjustment to a parameter. Lebey himself said that if these objects were confirmed, they represented a challenge to the standard model that could not easily be dismissed. Other astronomers reacted with a mixture of excitement and something closer to vertigo. Alison Kirkpatrick, a cosmologist at the University of Kansas, was direct about the emotional reality of the moment. She told reporters that she was having an existential crisis and that she was not using the phrase loosely. For someone who had built a career understanding how galaxies form and evolve, looking at the Webb data felt, she said, like watching the rules of physics break down in real time. Now, it is important to be honest about the scientific process here, because science is not a collection of dramatic revelations announced in clean moments. It is a long, grinding, often frustrating negotiation between what you observe and what you understand, and the early days of any new telescope's data are always messy. There were legitimate questions about whether the redshift estimates for some of these objects were accurate. Measuring a redshift precisely requires spectroscopic confirmation, not just photometric analysis, and early Webb observations relied heavily on the latter. There were questions about whether stellar mass estimates could be trusted given how unusual the star formation conditions in the early universe might have been. Some researchers cautioned that what looked like a single massive galaxy could turn out to be multiple overlapping sources at different distances. The scientific community did not simply declare the model broken and walk away. That is not how science works, and it is not what happened. What happened instead was a sustained, rigorous, increasingly anxious effort to find an explanation that fit within the existing framework. Astronomers proposed that perhaps star formation in the very early universe was dramatically more efficient than models predicted, that these early galaxies somehow converted their available gas into stars at a rate far higher than anything we observe today. Others proposed modifications to the initial power spectrum of density fluctuations, suggesting that perhaps the seeds of structure in the early universe were somehow larger or more numerous than the standard model predicts. Some researchers pointed to the possible role of massive black holes forming early and accelerating galaxy assembly around them in ways the models hadn't properly accounted for. These were serious proposals, offered by serious scientists doing exactly what serious scientists are supposed to do. But each proposed solution came with its own problems, its own tensions with other observations, its own reluctance to fit cleanly into the existing framework. And the data kept coming. Webb kept looking, and the anomalies kept appearing, and the spectroscopic confirmations, the ones that eliminated the possibility of simple measurement error, began to pile up. Galaxy after galaxy, at redshifts that put them in the first few 100 million years of cosmic history, displaying stellar masses and structural properties that Lambda CDM could not comfortably explain. By late 2023 and into 2024, the scientific conversation had shifted. The initial hope that the universe breakers would resolve themselves into something more manageable, that better data would show they were misidentified or mismeasured, was fading. Not because every anomaly survived scrutiny intact, because some didn't, and that is worth acknowledging, but because enough of them did. Enough of them passed spectroscopic confirmation. Enough of them remained stubbornly, uncomfortably real when examined with the most rigorous tools available. There is a particular kind of silence that falls in a scientific field when a well-established model begins to crack. It is not the silence of defeat. Scientists are not easily defeated, and the impulse to defend a successful framework is both natural and professionally rational. It is more like the silence that falls when a conversation you expected to go one way suddenly goes another, and everyone in the room is quietly recalculating. That silence was beginning to settle over cosmology. It is worth pausing here to feel the full weight of what this means, because the numbers can make the enormity of the problem abstract. The Lambda CDM model is not just one idea among many that cosmologists happen to prefer. It is the conceptual infrastructure of modern cosmology, the foundation on which virtually every major research program in the field is built. The design of telescope surveys, the interpretation of gravitational lensing maps, the predictions about dark matter distribution, the understanding of how the cosmic web of filaments and voids came to be, all of it rests on Lambda CDM. When physicists build a new instrument and point it at the sky, Lambda CDM tells them what they should expect to see. It is, in the deepest sense, the story humanity has told itself about how the universe grew up. And Webb, in its first months of operation, had found what looked like pages from a completely different story. There is an analogy that keeps coming up in discussions with cosmologists, and it is one of those analogies that is almost too apt to be comfortable. Imagine you are an archaeologist excavating a site, and your models of that civilization tell you very clearly that writing was not developed there until roughly the equivalent of 5,000 years ago. You begin digging carefully through the layers of sediment, working your way down through the strata, confident in what you know. And then, in a layer that should correspond to 20,000 years ago, you find a library. Not a primitive scratching on a cave wall, but a library, organized, structured, abundant with information. The first question is obvious. Did we get the dating wrong? You check it again, and the dating holds. The library is 20,000 years old, and it is real, and it is there, and now you have a problem that is much larger than the anomaly itself, because a library that old does not just violate one assumption. It begins to pull on every thread of your understanding of that civilization's entire history. Webb's early galaxies are the library. They don't just require a small revision to galaxy formation timelines. They challenge the physics of how quickly gravity can do its work, how efficiently gas can cool and collapse, how fast stars can form and die and enrich the surrounding medium with metals, how quickly all of that can be assembled into something large enough and structured enough to register as a mature galaxy. Each step in the chain has known physical timescales, and those timescales don't simply compress to accommodate what Webb was finding. The universe, according to the standard model, was not in a position to have done this work so quickly. The schedule doesn't allow for it. And yet there they were, sitting in the data, refusing to disappear. The universe breakers had entered the conversation. The phrase was journalistic, but the crisis it named was entirely real and entirely scientific. Something was wrong with the picture. The question was how wrong, whether this was a crack that could be repaired with modifications and new parameters, or whether it was the kind of crack that spreads, the kind that eventually forces you to admit that what you thought was a solid foundation is something else entirely. That question would not be answered by the galaxy data alone, because even as Webb was rewriting the early history of the cosmos, a completely separate body of evidence, one that had been building quietly for years before Webb ever launched, was pointing toward the same unsettling conclusion by a different route. It had been called, with admirable understatement, a tension, a disagreement between two different ways of measuring the fundamental expansion rate of the universe, a number that should have been the same no matter how you calculated it, and wasn't. It had been sitting in the data for years, modest and persistent, surviving every attempt to explain it away. And as Webb's anomalies deepened the unease in cosmology, that tension was about to become something that could no longer be politely ignored. The tension that wouldn't go away, so the galaxies were wrong. Their very existence, those massive, luminous, impossibly mature structures staring back at us from the universe's first few 100 million years, suggested that something in our fundamental story of cosmic evolution had cracked. But here is what made the situation genuinely unsettling for the scientific community. The galaxies were not the only thing that was wrong. They were simply the newest problem. Because running parallel to Webb's startling revelations, for years before the telescope ever left the ground, there had been another crisis quietly building in the data. A tension, one that had refused, no matter how many times brilliant people tried to resolve it, to go away, to understand it. You have to understand one number. A number that cosmologists treat the way engineers treat the speed of sound in a material they're designing around, as a fundamental property of the system, the thing everything else is calculated from. That number is called the Hubble constant. It is named for Edwin Hubble, the astronomer who, in the 1920s, first demonstrated that the faint smudges visible through telescopes were not clouds of gas within our own galaxy, but entire galaxies in their own right, island universes, each containing hundreds of billions of stars scattered across a space so vast the mind refuses to hold it. And then Hubble did something even more astonishing. He showed that these galaxies were moving away from us, not randomly, not chaotically, but systematically, in every direction, with a velocity that increased proportionally to their distance. The farther away a galaxy was, the faster it was receding. The universe, Hubble concluded, was expanding. The Hubble constant is simply the measured rate of that expansion. It tells you, for every unit of distance in space, specifically every megaparsec, which equals roughly 3¼ million light-years, how many kilometers per second faster a galaxy is moving away from you. It is a compression of the universe's entire expansion history into a single value, and for decades, measuring it precisely was considered one of the central problems of observational cosmology. Get that number right, and you could calculate the universe's age, its geometry, its ultimate fate. Now here is where the story splits into two roads, and where the trouble begins. There are two fundamentally different ways to measure the Hubble constant. The first looks backward, deep into the past, to the very edge of what light can tell us. In the early universe, roughly 380,000 years after the Big Bang, the cosmos had cooled just enough for electrons and protons to combine into neutral hydrogen atoms for the first time. Before that moment, the universe was an opaque plasma, light perpetually scattered and trapped. When neutrality arrived, light could finally travel freely, and it flooded outward in every direction. We can still detect that ancient light today. It has been stretched by billions of years of cosmic expansion into microwave radiation, and it fills the entire sky uniformly, a faint fossil glow called the cosmic microwave background. The European Space Agency's Planck satellite spent years mapping this background radiation with extraordinary precision, and embedded within its subtle temperature fluctuations, tiny ripples of density frozen into the light, is a kind of cosmological fingerprint. When you run the Lambda CDM model against those ripples, when you let the mathematics of the standard model interpret what it sees, you extract a Hubble constant of approximately 67.4 kilometers per second per megaparsec. The second road runs in the opposite direction. Instead of looking at light from the dawn of time, you look at objects nearby, relatively nearby, in cosmic terms, and you measure their distances and their speeds directly. This is called the cosmic distance ladder, and it is exactly what it sounds like. A sequence of overlapping measurement techniques, each calibrated against the one below it, climbing rung by rung outward into the universe. You start with the nearest stars, whose distances can be measured geometrically by watching how they shift against the background sky as Earth orbits the Sun, a method called parallax. From those stars you calibrate Cepheid variables, giant pulsing stars whose rate of brightening and dimming is directly tied to their intrinsic luminosity, making them reliable cosmic beacons. With Cepheids you can reach into other galaxies, and from those galaxies you calibrate Type 1a supernovae, catastrophic stellar explosions so consistent in their peak brightness that astronomers call them standard candles. With supernovae, you can reach billions of light-years into the universe and read off its expansion rate directly from the data. When you climb that ladder and measure the Hubble constant the local way, you get approximately 73 kilometers per second per megaparsec, 67.4, 73, a gap of roughly 9%. Now, 9% might not sound like much. In everyday life, a 9% discrepancy in almost anything would be considered a rounding error, a minor inconsistency, something easily explained away. But in cosmology, where measurements have been refined over decades with instruments calibrated to extraordinary precision, where the error bars on both of these values have been shrunk to the point where they barely overlap at all, 9% is not a rounding error. 9% is a scream, and the person who has perhaps heard that scream most clearly, who has spent more of his professional life standing in front of it than almost anyone else alive, is a Johns Hopkins University astronomer named Adam Riess. Riess came to prominence in 1998 as part of one of the most dramatic discoveries in the history of science. He and his team, along with a competing group led by Saul Perlmutter, were using Type Ia supernovae to map the universe's expansion history, not just how fast it's expanding now, but how that rate has changed over time. The assumption going in was reasonable and intuitive. Gravity should be slowing the expansion down. The Big Bang had hurled matter outward, but gravity was pulling it back. And eventually the thinking went, expansion would decelerate, stop, or even reverse into a big crunch. What Riess found instead was the opposite. The expansion of the universe was not slowing down. It was accelerating. Something was pushing space apart with increasing force. Something that had no place in the existing equations. Something they eventually named dark energy. It was an extraordinary discovery, so counterintuitive and so thoroughly confirmed that in 2011, Riess, Perlmutter and their colleague Brian Schmidt were awarded the Nobel Prize in Physics. But Riess did not stop there. He became obsessed with precision. If the universe was accelerating, if dark energy was real, then measuring the Hubble constant with absolute accuracy was more important than ever. He founded a project called SH0ES, supernovae, and H0 for the equation of state, dedicated entirely to climbing the distance ladder as carefully as humanly possible and pinning down the Hubble constant with the tightest possible error bars. For years, his team refined their Cepheid calibrations, cross-checked their supernova data, looked for every possible systematic error, and eliminated them one by one. And every time they finished, the answer came back the same: 73. Meanwhile, the Planck satellite finished its own work, and its answer came back equally firm: 67.4. Early on, the scientific community was calm about it. The gap was real, but at the level of what statisticians call 2 sigma, meaning the discrepancy was about 2 standard deviations beyond what random measurement error could explain. That sounds significant, but in physics, 2 sigma is considered weak evidence. It happens by chance relatively often. Most physicists assumed that as the measurements improved, the tension would dissolve. One team or the other would find a systematic error, something they'd overlooked, and the 2 values would converge. They did not converge, they diverged. As Ries's team published refinement after refinement, as other independent groups using entirely different methods, gravitational lensing of distant quasars, the brightness of giant red stars, the oscillations of the cosmic web itself, came in with their own measurements, the tension climbed from 2 sigma to 3, from 3 to 4. By the early 2020s, the discrepancy had crossed 5 sigma. 5 sigma is a threshold with a specific meaning in physics. It is the point at which a result is no longer called an anomaly or a hint. It is called a discovery. When physicists detected the Higgs boson at the Large Hadron Collider in 2012, they waited until their signal crossed 5 sigma before announcing it to the world, because 5 sigma means the probability of the result occurring by random chance is less than 1 in 3.5 million. When the Hubble tension crossed that line, it was no longer possible to dismiss it as statistical noise. Something was genuinely wrong. And now, with the most recent measurements incorporating data from the James Webb Space Telescope, the same instrument that had already shattered expectations with those impossible early galaxies, the tension is approaching 9 sigma. The probability that this discrepancy is a fluke is so vanishingly small that it has essentially no mathematical meaning. It is not an error in the data. It is not a flaw in the instruments. Both measurement methods have been checked and rechecked by independent teams with independent tools and independent assumptions, and they keep arriving at incompatible answers. This is the moment the story becomes genuinely strange, because there is an implication lurking inside this disagreement that most popular accounts of the Hubble tension shy away from stating plainly. If both measurements are correct, and there is no credible evidence that either is wrong, then the universe cannot be described by a single coherent model. The Planck satellite is measuring the expansion rate of the early universe, extrapolating it forward using Lambda CDM. Ries is measuring the expansion rate of the late universe directly. If those 2 things genuinely disagree, it means the universe did not evolve the way Lambda CDM says it did. Something happened between the early universe and now that the model does not account for. Some ingredient is missing, or some assumption built into the foundation of modern cosmology is false. It was somewhere in the weight of this realization, in the accumulation of data from his own project, now reinforced by Webb, now confirmed by multiple independent lines of evidence, that Adam Riess is said to have spoken 4 words that have since haunted the edges of cosmological discussion. 4 words not written in a paper, not delivered in a lecture, but reportedly spoken in the unguarded moment of confronting what his own numbers actually meant. This isn't our universe. It is worth sitting with what that sentence actually means, because it is not a poetic flourish. It is not despair. It is a precise scientific statement, and its precision is what makes it so deeply unsettling. What Rees meant, what those 4 words compress into their quiet devastation, is that the universe described by our best cosmological model and the universe revealed by direct observation are not the same universe. The Lambda CDM model is extraordinarily successful. It predicted the large-scale structure of the cosmic web. It predicted the fluctuations in the cosmic microwave background to stunning accuracy. It has passed test after test for decades. And yet when you use it to calculate how fast the universe should be expanding right now, and then go look at how fast it is actually expanding right now, you get numbers that disagree at a level no physicist can any longer dismiss. The model and reality have parted ways. The options for what this means are all uncomfortable. The first is that there is new physics operating in the universe, some additional ingredient, some force or field or phenomenon that the standard model does not include, that has been altering the expansion rate in ways we have not yet accounted for. This would be scientifically exciting, but it would also mean that decades of cosmological calculation have been built on an incomplete foundation. The second is that there is something wrong with the cosmic microwave background interpretation, that Lambda CDM's reading of that ancient light is flawed in some subtle way, perhaps because the model itself contains an assumption so deep we haven't thought to question it. The third option is perhaps the strangest, that the universe has no single consistent expansion history, that its behavior has changed in ways that break the assumption of uniformity underlying all of modern cosmology. Any one of these would be, in Rias's own words, extraordinary. Together, arriving simultaneously alongside Webb's galaxy problem, they represent something that careers are built on and textbooks are rewritten around. And yet the scientific community has not fully reckoned with what this implies. There have been proposed solutions, of course. There are always proposed solutions. Physicists have suggested early dark energy, a hypothetical burst of energy in the early universe that could have boosted the expansion rate just enough to reconcile the numbers. They have proposed modifications to general relativity, new particles, interacting dark energy models, decaying dark matter. Each of these papers is clever, mathematically rigorous, and fascinating. And each of them, when tested against the full range of observational data, fails to resolve the tension completely without breaking something else. This is what physicists mean when they talk about a crisis. Not that they are panicking, not that they are lost, but that the toolkit they have relied on for half a century is producing answers that contradict themselves, and no one yet has a tool that can bridge the gap. So we have two wounds now, two places where the standard model bleeds. The Webb galaxies appearing too early, too massive, too bright, violating the timeline of structure formation, and the Hubble tension, two independent measurements of the same universe arriving at different universes, a 9% fracture in the fabric of cosmological consensus. And here is what makes them genuinely terrifying to think about together. They are not obviously connected. They are not two symptoms pointing to the same illness. They are anomalies from different epochs measured by different methods pointing, perhaps, at different failures. Which means the problem might not be one missing ingredient, it might be the recipe. And sitting at the center of that recipe, the single most important number in the entire Lambda CDM framework, the number that determines the geometry of space, the rate of expansion, the fate of everything, is the cosmological constant. The value Einstein introduced, removed, and called his greatest blunder. The value that was resurrected to explain dark energy, the value that Rees's Nobel Prize-winning work helped put back on the table. That constant has its own problem, one that physicists have known about for decades and chosen, perhaps not wisely, to quietly endure. Because when you calculate what the cosmological constant should be from first principles, when you let quantum mechanics tell you how much energy empty space contains, you get a number that is so obscenely, catastrophically different from the one we observe that it makes the 9% Hubble tension look like a minor accounting discrepancy. That calculation, that gap, that silence at the center of theoretical physics where an answer should be, that is where we are going next. So we've been sitting with a paradox. Two methods of measuring the universe's expansion rate, both precise, both rigorous, both arriving at numbers that refuse to agree. And for years, cosmologists told themselves this was a measurement problem, a calibration error hiding somewhere in the data. Something that better instruments, sharper observations, more careful analysis would eventually resolve. But the better the instruments got, the more stubbornly the tension held. And now, just as astronomers were beginning to seriously entertain the idea that something might be genuinely fundamentally wrong with the model itself, a completely different instrument, pointing at a completely different aspect of the cosmos, delivered a result that didn't just deepen the crisis. It threatened to pull the entire framework apart at the seams. To understand what happened, you need to understand what dark energy actually is, or rather, what we've been assuming it is. Because that assumption, it turns out, may be the most consequential mistake in the history of modern physics. Cast your mind back to 1998. Two independent teams of astronomers were studying supernovae, specifically a type called Type Ia supernovae. These stellar explosions are remarkable because they always detonate with almost exactly the same intrinsic brightness. This makes them extraordinarily useful as what astronomers call standard candles. If you know how bright something actually is, and you measure how bright it appears from Earth, you can calculate precisely how far away it is. The teams were using these supernovae to map the expansion history of the universe, expecting to find that gravity was gradually slowing everything down since the Big Bang. What they found instead stopped physics in its tracks. The universe wasn't slowing down. It was accelerating. Something was pushing space itself apart, and whatever it was winning against gravity at cosmic scales. The discovery was so shocking, so counterintuitive, that it earned its discoverers the Nobel Prize in Physics in 2011. And to explain this acceleration, physicists reached for something that had been sitting in Einstein's equations for decades, largely forgotten and somewhat embarrassing. They reached for lambda, the cosmological constant. Here's where the story becomes genuinely ironic. In 1917, Einstein was trying to build a static model of the universe using his newly completed theory of general relativity. The equations kept producing a universe that either expanded or contracted, which troubled him because at the time most scientists believed the cosmos was eternal and unchanging. So he added a term to his equations by hand, a kind of mathematical counterweight against gravity, a repulsive force distributed uniformly throughout all of space that would hold the universe in equilibrium. He called it the cosmological constant. Then, in 1929, Edwin Hubble discovered that galaxies were receding from us in all directions. The universe was expanding. It wasn't static at all. Einstein's justification for adding lambda vanished overnight. He reportedly called it his greatest blunder. The constant was quietly removed from the equations and filed away as a curiosity. Then 1998 arrived, and suddenly the greatest blunder didn't look like a blunder anymore. It looked like a prediction. The cosmological constant, reinterpreted as the energy density of empty space itself, what physicists now call vacuum energy, seemed to explain the accelerating expansion perfectly. The mathematics worked. The fit to the data was excellent. Lambda was stitched back into the model and given a place of honor at the center of cosmology. The Lambda CDM model, combining this cosmological constant with cold dark matter, became the standard framework, the bedrock, the thing you had to have a very good reason to question. But there was always a quiet, unsettling problem lurking underneath this triumph. Lambda, by definition, is a constant. It doesn't change. It was the same at the beginning of the universe as it is today, and it will be the same in 1 trillion years. It's baked into the structure of space-time itself. And this seemingly simple assumption that the energy driving cosmic acceleration is fixed and eternal is what the universe may now be telling us is wrong. Enter DESI. The dark energy spectroscopic instrument is, in a word, extraordinary. Mounted on the 4-meter Mail telescope at Kitt Peak National Observatory in Arizona, it operates using 5,000 robotic fiber optic sensors, each one capable of being positioned with extraordinary precision to capture the light from a specific galaxy. Each night, it stares at the sky and collects the light signatures of tens of thousands of galaxies simultaneously, measuring their spectra, the way their light has been stretched and shifted by the expansion of the universe, allowing astronomers to determine their distances with remarkable accuracy. The ambition of the project is almost hard to comprehend. DESI is constructing the largest three-dimensional map of the universe ever attempted, cataloging the positions of tens of millions of galaxies across billions of light-years of cosmic history. And what it uses that map to measure is something called baryon acoustic oscillations. This sounds technical, but the underlying idea is beautiful. In the earliest moments of the universe, before atoms had even formed, the cosmos was a hot, dense plasma of particles. Sound waves propagated through this plasma, pressure waves carrying energy outward in expanding spheres. When the universe cooled enough for atoms to form, about 380,000 years after the Big Bang, this plasma froze. The sound waves stopped. And wherever the leading edge of those expanding spherical waves happened to be at that moment, matter was slightly denser. Those slight overdensities became preferred locations for galaxies to form. The result is a characteristic scale imprinted across the large-scale structure of the universe, a preferred clustering distance between galaxies of about 500 million light-years. This preferred scale, this frozen acoustic signature, is our ruler. By measuring how this scale changes at different distances, and therefore at different points in cosmic history, DESI can trace how the expansion rate of the universe has evolved over billions of years with precision that no previous instrument has achieved. In April 2024, DESI released its first year of results. The team had mapped approximately 6 million galaxies, and the data contained something that sent a tremor through the cosmological community. The signal wasn't a screaming alarm. It was quieter than that, and in some ways more disturbing because of it. When the DESI team fitted their baryon acoustic oscillation measurements to models of dark energy, they found something that deviated from a pure cosmological constant at what statisticians call 2.5 sigma confidence. Now, 2.5 sigma is not the 5 sigma threshold that physicists require before declaring a discovery. It is not by itself proof of anything, but it is far too significant to dismiss. In scientific terms, a 2.5 sigma result means there is roughly a 1 in 80 chance the deviation is due to random chance alone, and what the deviation pointed toward was deeply unsettling. Dark energy appeared to be evolving over cosmic time. Specifically, it appeared to have been stronger in the past and to be weakening as the universe ages. To capture this possibility mathematically, cosmologists use what's called the W0WA parameterization, a framework for allowing dark energy's properties to vary over time rather than remaining fixed. In this system, W0 describes dark energy's behavior today, and WA describes how that behavior changes as you look back through cosmic history. For a pure cosmological constant, the values are exactly -1 for W0 and exactly 0 for WA. Perfectly frozen, perfectly constant. When DESI's team plugged their data into this framework, the best fit values they obtained were not those numbers, they were shifted. The data preferred a picture in which dark energy was more intense in the earlier universe and has been gradually losing its strength as cosmic time has passed. Think about what this means for a moment. The cosmological constant was our explanation for why the universe is accelerating. If dark energy is not a constant but something that fades, then its future behavior becomes genuinely unknowable without a new theory to replace lambda. And more alarming still, if dark energy continues to weaken, there is a scenario in which it weakens enough that the expansion of the universe stops accelerating or even reverses. Gravity, patient and relentless, could eventually begin to win. The grand, cold, forever expanding cosmos that our current model predicts, with galaxies drifting apart over trillions of years until nothing can reach anything else, might not be the real future at all. There is a version of this story that ends not in a quiet, frozen darkness, but in a collapse, a reversal, a big crunch. But that's not the only alternative the data suggests. There are other models of dark energy that cut in a different direction entirely, and some of them are, if anything, more destabilizing than collapse. Quintessence is the oldest and most studied alternative. It posits that dark energy isn't vacuum energy at all, but rather a dynamic field, something like a fluid permeating all of space, but one that can evolve and change. Quintessence fields can be constructed to weaken over time, which aligns with what DESI appears to be seeing, but they can also be constructed to do almost anything, which is both their appeal as a modeling tool and their weakness as an explanation. A theory that can fit any data doesn't really explain anything, it just accommodates it. Then there is phantom energy, which sits on the other side of the mathematical divide. Phantom models predict dark energy that grows stronger over time, leading eventually to a scenario called the Big Rip. In this picture, the accelerating expansion of space becomes so intense that it eventually overcomes not just the gravity holding galaxy clusters together, but the forces binding galaxies themselves, then solar systems, then planets, then atoms. Everything is eventually torn apart by the expansion of space at scales that currently only apply to the distances between galaxy clusters. The DESI data, with its suggestion of weakening dark energy, appears to disfavor pure phantom models, but the mathematical framework allows for dark energy that oscillates, that was phantom-like in the past and quintessence-like now, or some combination. The parameter space of possibilities is enormous. There is also a class of proposals called early dark energy, which attempt to solve a related problem. You'll remember from our earlier discussion that the two methods of measuring the Hubble constant produce conflicting values. Early dark energy models try to resolve this tension by proposing a brief burst of dark energy in the first moments of the universe's history, before it faded into the background behavior we observe today. Some versions of early dark energy are actually consistent with the DESI findings, offering a tantalizing possibility that a single new piece of physics might resolve multiple crises simultaneously. But no proposed model has yet achieved this cleanly. Every attempt to fix one tension seems to create strain somewhere else in the framework. And here is perhaps the most profound consequence of what DESI has found, or more precisely, what it has questioned. If dark energy is not a constant, then the entire history of the universe that we've reconstructed from our observations may need to be revised. The age of the universe, currently calculated at about 13.8 billion years, depends on the expansion history. If that history is different from what Lambda CDM assumed, the age estimate changes. The distance to the most remote objects we've ever observed, distances that depend on our model of how expansion has proceeded over time, those distances change. The total size and geometry of the observable universe, inferred from the same model, would need recomputation. The fate of the universe, whether it ends in frozen darkness or something far more dramatic, becomes an open question again. We built an extraordinarily precise picture of the cosmos. We measured its age to within 100 million years. We mapped its large-scale structure across billions of light years. We calculated the proportions of ordinary matter, dark matter, and dark energy to within fractions of a percent. And we built all of this on the foundation that lambda was exactly what Einstein accidentally introduced: a fixed universal number, the same in all places and at all times. And now the data from 6 million galaxies is whispering that the foundation might have a crack running through it. This is the deep irony that Einstein could never have anticipated. He added the cosmological constant as a convenience, a mathematical patch to preserve a universe he wanted to believe in. He was wrong about the static universe, and he knew it, and he considered the constant a blunder because of what it represented: a willingness to distort a beautiful theory to match a comfortable assumption. And then we reintroduced it for different reasons, also compelling, also mathematically elegant, also fitting the data beautifully, but perhaps also in some way we don't yet fully understand, also wrong. Not wrong in the way Einstein was wrong, because the accelerating expansion is real and confirmed beyond any doubt, but wrong in assuming that the thing driving the acceleration is simple and constant and eternal. There's a particular kind of scientific vertigo that sets in when you realize that the most successful model in the history of cosmology might be built on an error of assumption rather than an error of measurement. It doesn't mean the model fails entirely. Lambda CDM gets so much right. The cosmic microwave background, the formation of large-scale structure, the abundance of light elements forged in the first minutes after the Big Bang. These predictions work with stunning precision. But a model can be a very good approximation to reality without being the final truth. And the places where the approximation breaks down, those small, stubborn deviations, those tensions that won't resolve, those galaxies that appear too early and expansion rates that won't agree and dark energy that refuses to stay constant, those are the fingerprints of something deeper, something the current model cannot see. And if dark energy is dynamic, if it changes, if it has a history rather than being merely a fixed property of spacetime, then it becomes a thing that demands an explanation. A cosmological constant requires no explanation beyond its existence. It simply is, but something that evolves must evolve for a reason. It must be part of some larger mechanism, connected to some deeper physics that governs its behavior. And the moment you ask what that physics might be, you walk directly into one of the most disturbing rooms in all of science. Because there is a calculation that every physicist knows about, and most of them would rather not discuss in public, or at least not without careful qualification. It is a calculation that sits at the intersection of quantum mechanics and general relativity, the two great pillars of modern physics, and it produces a number so catastrophically wrong that it has been called the worst prediction in the history of science. It is a calculation about the energy of empty space itself. And if dark energy is not a fixed constant but something that can vary, then this calculation, and what it implies about why the universe's dark energy has the extraordinary precise value it actually does, becomes not just a theoretical puzzle, but an urgent and perhaps unanswerable question. Because the value dark energy has, whatever its source, cannot be an accident. The universe you're sitting in right now, the one with stars and planets and chemistry and life, depends on dark energy being almost inconceivably precisely tuned. Slightly larger, and the universe would have expanded so fast that gravity could never have pulled matter into galaxies. Slightly smaller, and it would have collapsed long before any of this could exist. And the gap between what the universe requires and what the naive calculation predicts is not small. It is not a rounding error. It is a discrepancy of roughly 120 orders of magnitude. The largest gulf between theory and observation in the entire history of physics. That number, what it means, and why some of the most serious physicists alive believe it points towards something far stranger than simply a new dark energy model. That is where we have to go next. So we've arrived at a problem that doesn't just challenge cosmology. It challenges something far deeper. It challenges the very notion that the universe we inhabit could have existed at all. Set aside for a moment the galaxies that appeared too early. Set aside the Hubble tension and the slow unraveling of the cosmological constant. Those are cracks in our models, serious ones, perhaps fatal ones. But the problem we're about to enter isn't a crack, it's an abyss, and the further you look into it, the more unsettling it becomes. Here is the situation as it stands. Modern physics rests on what we call the Standard Model, our most complete and accurate description of reality at its most fundamental level. It describes the particles that make up everything you can see, touch, or measure, and the forces that govern how they interact. And embedded within this model are 26 numbers. 26 dimensionless constants, quantities with no units, no derivable cause, no theoretical justification for the values they hold. Numbers like the fine structure constant, which governs the strength of electromagnetic interactions, the ratio of the electromagnetic force to the gravitational force, the mass ratios of elementary particles, the cosmological constant that we spent the last chapter watching unravel. These numbers cannot be calculated. They cannot be derived from deeper principles. They cannot be predicted by any equation we currently possess. They can only be measured, observed from the universe itself, plugged into our equations by hand, and accepted. No one knows why they are what they are. No theory tells us they had to be this way. They simply are. And that silence, that absence of explanation, is where the trouble begins. Because when you start asking what happens if those numbers were different, even slightly different, you discover something that stops physicists in their tracks. Something that has driven careers, fractured philosophical commitments, and pushed some of the most rigorous scientific minds into territory they never expected to enter. The universe, it turns out, is balanced on a knife's edge, and the knife is impossibly thin. Take the cosmological constant, the value that represents the energy density of empty space, the same constant whose instability we've been tracking. Its observed value is extraordinarily small, vanishingly, almost absurdly small. Quantum field theory, which governs the behavior of subatomic particles, predicts that the vacuum energy of space should be enormous, roughly 10 to the power of 120 times larger than what we actually observe. That's not a rounding error. That's not a measurement uncertainty. That's a discrepancy of 1 followed by 120 zeros. The largest mismatch between theory and observation in the entire history of physics. And yet, if the cosmological constant were anywhere near the value that quantum field theory naively predicts, the universe would have torn itself apart before a single atom could have formed. Space would have expanded so violently, so instantaneously, that matter could never have clumped together. There would be no galaxies, no stars, no planets, no chemistry, no time in any meaningful sense for anything to happen. Alternatively, if the constant were negative by a similar magnitude, the universe would have collapsed back on itself in a fraction of a second after the Big Bang. Not billions of years, a fraction of a second. The value we observe is tuned to 1 part in 10 to the 120th power. Write that as a probability and the paper isn't big enough. It's not just the most extreme fine-tuning problem in physics. It is, by a staggering margin, the most extreme fine-tuning problem in all of human knowledge, and we have no explanation for it. But the cosmological constant is not alone in this. It is the most dramatic example, but it is surrounded by companions equally improbable, equally unexplained. Consider the ratio of the electromagnetic force to the gravitational force, a number approximately 10 to the power of 36. Gravity is that many times weaker than electromagnetism. This seems like an accident of cosmic proportions, but if that ratio were significantly different, stars couldn't exist as they do. Either they would burn through their fuel in years rather than billions of years, giving no time for planets to form and life to emerge, or they would never ignite at all. The specific weakness of gravity is what gives stars their extraordinary longevity, their ability to burn steadily for billions of years, nurturing the possibility of complex chemistry on worlds orbiting them. Or consider the strong nuclear force, which binds quarks into protons and neutrons into atomic nuclei. Increase its strength by just a few percent, and hydrogen, the simplest element, the fuel of stars, the building block of water, becomes unstable. It fuses immediately into helium and beyond, and a universe without hydrogen is a universe without the most fundamental step in stellar chemistry. Decrease it by a similar fraction and protons and neutrons don't bind at all. No nuclei, no atoms beyond hydrogen. No periodic table, no complexity of any kind. The pattern repeats across every fundamental constant you examine. Each one sits in an extraordinarily narrow window, a window so narrow that the word coincidence begins to feel not just inadequate, but almost offensive to the mathematics. And then there is the story of Fred Hoyle. Because if you want to understand what fine-tuning truly means, you need to understand what happened to a man who spent his life trying to explain the universe without any hint of design. Hoyle was one of the 20th century's great astrophysicists, a brilliant, combative, fiercely independent thinker who made foundational contributions to our understanding of how stars forge the elements. He was also, by his own declaration, a committed atheist and materialist. The universe for Hoyle was a machine, extraordinary in its complexity, but explicable in principle through physics. No designer required, no purpose embedded in the structure of things. In the 1950s, Hoyle was working on the theory of stellar nucleosynthesis, the process by which stars create the heavy elements that make up the world around you. Carbon is the backbone of all known life. Every carbon atom in your body was forged in the heart of a dying star. The process by which stars create carbon involves a specific nuclear reaction, a collision between 3 helium nuclei to form carbon-12. But this reaction should, by all rights, be fantastically improbable. 3 particles meeting simultaneously in exactly the right configuration is an incredibly unlikely event. Hoyle realized that for carbon to exist in the universe, in anything like the abundances we observe, the carbon-12 nucleus would need to possess a very specific property, what physicists call a resonance state, an energy level at which the nucleus vibrates in a way that dramatically enhances the probability of that 3-body collision. He calculated what that energy level would have to be. He then went to the experimental physicists at Caltech and told them, in effect, go look for this, it has to be there, because if it isn't, we don't exist. They found it, exactly where Hoyle had predicted. A resonance in carbon-12 at approximately 7.656 million electron volts, a number that sits with extraordinary precision in the narrow range that allows the reaction to proceed and the universe to be filled with carbon. Now here is what makes this story remarkable, genuinely remarkable in a way that transcends the physics. Fred Hoyle, the committed atheist, the lifelong materialist, was so disturbed by what he had found that he publicly stated, in terms he never retracted, that the universe looks like a put-up job. That is not the language of a man who found a satisfying natural explanation. That is the language of a man staring into something he cannot account for. He later wrote that a common-sense interpretation of the facts suggests that a super-intellect has monkeyed with physics, as well as with chemistry and biology. For Hoyle, who had built his career on exactly the opposite philosophical conviction, this was an extraordinary admission. He didn't become religious, but he became something perhaps more unsettling. A scientist who had followed the evidence to a place where the evidence refused to be comfortable. So how does mainstream science respond to this? What is the official answer, the peer-reviewed, institutionally acceptable framework for explaining why the constants of nature appear calibrated with such terrifying precision? The primary tool is the anthropic principle, and it comes in two forms that are worth understanding carefully, because one is subtle and the other is deeply controversial. The weak anthropic principle is, at its core, a straightforward observation. We observe the universe to have the constants it has because only in a universe with approximately those constants could observers like us exist to do the observing. It's a selection effect. Of course, we find ourselves in a universe compatible with our existence. We couldn't be anywhere else. We can't observe a universe that didn't produce us. This isn't a law of physics, it's a logical necessity, and it's entirely valid as far as it goes. The problem is how far it goes. The weak anthropic principle doesn't explain why a universe with life-permitting constants exists. It only points out that if one does, life will observe it. It answers no question about origin or probability. It's a statement about the limits of our observational sample, not a mechanism. Many physicists find it not so much wrong as empty, correct but unhelpful, like explaining why you survived a car accident by noting that dead people don't report accidents. The strong anthropic principle is more ambitious and far more contentious. It holds that the universe must have constants that permit the existence of observers, that there is some fundamental connection between the existence of consciousness or complexity and the parameters of physical law. This begins to sound less like physics and more like philosophy, or perhaps something older than both. It has attracted fierce criticism from scientists who regard it as untestable and therefore unscientific. It answers the fine-tuning problem by essentially declaring it necessary, which feels to many like naming the mystery rather than solving it. And so, searching for a more mechanistic escape route, a significant portion of theoretical physics has turned to the multiverse. The argument runs like this: if there exists not one universe, but an effectively infinite collection of universes, each with different values for the fundamental constants, then fine-tuning ceases to be a mystery. In an infinite ensemble of universes exploring every possible combination of physical laws, some universes will inevitably have the right constants for complexity and life. We find ourselves in one of those for the same reason the weak anthropic principle identifies: we couldn't be anywhere else. The cosmic lottery isn't rigged, it's just that with enough tickets, someone always wins. This idea draws support from two directions in modern theoretical physics. The first is string theory, which attempts to be a fundamental theory of everything, a framework that unifies quantum mechanics and gravity. String theory predicts a vast landscape of possible solutions, each corresponding to a different set of physical laws and constants. The number of possible string theory vacua is estimated at 10 to the power of 500. That's not 10 to the 500 universes, it's 10 to the 500 possible configurations of physical law, an almost incomprehensibly large menu of possible realities. The second direction comes from inflationary cosmology, the theory that in the first fraction of a second after the Big Bang, the universe underwent a period of extraordinarily rapid expansion. Many versions of inflation are, in a technical sense, eternal. Once inflation begins, it tends to keep going in different regions, spawning bubble universes that pinch off into separate realities, each potentially with different physics. The cosmological multiverse generated by eternal inflation is, in the mathematics, essentially unbounded. Together, these frameworks offer physics its escape from the fine-tuning abyss. If there are effectively infinite universes with all possible constants, we need not explain why our constants are what they are. We need only note that life-bearing universes will be observed by the life they bear. But here is the problem, and it is a serious one that no amount of mathematical elegance resolves. A theory that predicts everything effectively predicts nothing. If the multiverse contains universes with every possible set of physical laws, then no observation you could make would be inconsistent with it. Every outcome, every measurement, every cosmological discovery confirms the theory, because every possible outcome exists somewhere in the ensemble. A framework that cannot be falsified, that can accommodate any result, is not a scientific theory in the traditional sense. It is, critics argue, more closely related to metaphysics. This is not a fringe objection. It is pressed by serious, accomplished physicists. Paul Steinhardt, one of the original architects of inflationary theory, has argued forcefully that eternal inflation and the multiverse it spawns have made cosmology unfalsifiable in a way that should alarm the scientific community. George Ellis and Joe Silk, both distinguished cosmologists, published a paper in Nature arguing that if theories like the multiverse cannot be tested or falsified, physicists need to have a serious conversation about what science actually is. These are not outsiders. These are people who built the field, and they are deeply uneasy. So where does this leave us? We have 26 numbers we cannot explain. We have fine-tuning so extreme, particularly in the cosmological constant, that the word improbable has to be stretched beyond ordinary meaning to contain it. We have the story of Fred Hoyle, a man whose philosophical convictions were overturned by his own discovery. We have the Anthropic principle, which is either a useful logical observation or an empty tautology, depending on who you ask. And we have the multiverse, which solves the problem only by inflating it into infinity and surrendering the possibility of ever being proven wrong. What is striking, genuinely striking, when you step back from the details, is that fine-tuning is not a problem that more data obviously solves. The tension in the Hubble constant might dissolve if we build better instruments. The early galaxies Webb observed might fit a revised model of galaxy formation. These are empirical problems, in principle resolvable through better measurement. But the fine-tuning problem gets sharper as our measurements improve. Every time we pin down the value of a fundamental constant with greater precision, we discover more exactly how razor-thin the margin for error truly is. Better physics, in this case, has made the mystery more acute, not less. And there is something quietly devastating in that pattern. The tools we've built to understand the universe have not resolved the deepest question, why is the universe the way it is, rather than some other way? They have only illuminated the question more starkly, made its dimensions more precise, and highlighted how thoroughly our current frameworks fail to answer it. We are not lacking in mathematics. We are not lacking in computational power or experimental precision. What we seem to be lacking is something more fundamental, a framework capable of addressing why the universe has the parameters it has at all. And in the absence of that framework, physics arrives at a particular kind of silence. Not the silence of ignorance, not the silence before we began exploring. A different kind of silence. The silence that falls after you have asked every available question through every available method, and found the question still standing unmoved, regarding you with the same patience it had before you began. It is that silence we need to examine next, because it turns out to be less empty than it first appears. So here we are, staring into an abyss of numbers that don't add up, constants that couldn't be otherwise, and a universe so precisely calibrated that the word coincidence starts to feel like an insult to mathematics. We've established that the cosmological constant is tuned to 1 part in 10 to the power of 120. We've seen that 26 fundamental numbers underpin everything that exists, and that none of them have a reason to be what they are. You might expect that somewhere in the architecture of modern physics there's a deeper theory waiting, something that explains the fine-tuning, that dissolves the mystery and replaces it with understanding. There isn't. What there is, instead, is silence. A very specific, very unsettling kind of silence that happens when you push our two greatest theories to their limits and watch them both fall apart at exactly the same moment. Physics has two pillars, not one, two, and they cannot both be right. The first pillar is general relativity, Einstein's theory of gravity, space, and time. It describes the universe at its largest scales with almost supernatural accuracy. The orbit of Mercury, the bending of starlight around the Sun, the existence of gravitational waves rippling across billions of light years, all of it confirmed, all of it precise. General relativity is one of the most tested theories in the history of human thought, and it has never once failed a test we've been able to conduct. The second pillar is quantum mechanics, the theory of the very small. It describes the behavior of subatomic particles, the structure of atoms, the nature of light, and the forces that bind matter together. Without it, we couldn't build semiconductors, lasers, or MRI machines. Quantum field theory, its more sophisticated descendant, is arguably the most accurate scientific theory ever constructed. It predicts the magnetic moment of the electron to 11 decimal places, a precision equivalent to measuring the distance from New York to Los Angeles and being accurate to within a single human hair. Both theories are correct. Both theories are, in their respective domains, essentially perfect, and they are fundamentally, mathematically incompatible with each other. This isn't a minor technical dispute waiting to be ironed out. This is a foundational crack running through the entire edifice of modern physics. When you try to apply quantum mechanics to gravity, when you try to build a theory of quantum gravity, the mathematics doesn't just struggle, it explodes. The equations produce answers of infinity, not very large numbers, infinity. And in physics, infinity is not an answer. Infinity is a signal. It means the theory is telling you it has reached the edge of its own validity. It means the map has run out of territory. The clearest place to see this breakdown is also the place it matters most, the beginning of everything. Wind the universe backward using general relativity, and you arrive at the Big Bang, a moment of infinite density, infinite temperature, infinite curvature of spacetime, a singularity. Now, the word singularity sounds technical and perhaps manageable, but what it actually means is deeply troubling. It means the equations of general relativity, the equations we use to describe the origin of our universe, produce a result of infinity at the very moment of creation. The theory destroys itself precisely when we need it most. It's as if you tried to use a calculator to understand the first instant of time, and the calculator simply ceased to function and handed you back a note reading, "This question cannot be answered here." Our universe's origin is, quite literally, outside the reach of known physics. That sentence deserves a moment. We do not know what created the Big Bang. We do not know what, if anything, came before it. We do not know whether time itself had a beginning, or whether that question even makes sense. General relativity, the theory that governs spacetime, breaks down at the very boundary of spacetime. Quantum mechanics, the theory of the smallest scales, might in principle help, but when you try to apply quantum theory to the singularity, you discover that the two frameworks produce contradictory descriptions of what a singularity even is. The silence at the beginning of the universe is not a silence we can fill, not yet, perhaps not ever, with our current tools. This same problem appears again, even closer to home, in an object you've almost certainly heard of, the black hole. At the center of every black hole, according to general relativity, there is another singularity, another point of infinite density, infinite curvature, where the equations again break down and give no useful answer. But black holes present a second crisis that is, in some ways, even more disturbing. This one doesn't come from general relativity alone. It comes from the collision between general relativity and quantum mechanics, a collision that has remained unresolved for 50 years, and that cuts to the heart of what the universe is made of. Stephen Hawking showed in 1974 that black holes are not completely black. Quantum effects near the event horizon, the boundary beyond which nothing can escape, cause black holes to slowly radiate energy and particles. This radiation is now called Hawking radiation, and it is widely accepted as correct, even though it has never been directly observed, because it follows inevitably from combining general relativity and quantum field theory. Black holes, Hawking demonstrated, slowly evaporate. Over incomprehensibly long timescales, far longer than the current age of the universe, a black hole loses mass and eventually disappears entirely, and here the crisis begins. Quantum mechanics has a rule, one of its most sacred rules. It is called unitarity, and it states, with no exceptions, that information is never destroyed. The total information content of a physical system is conserved. If you burned a book, the ash and smoke and light and heat would in principle still contain all the information that was in the book. You could never recover it practically, but it would still exist. Information in quantum mechanics is eternal. When matter falls into a black hole, it carries information with it. The particular arrangement of every atom, every particle, every quantum state. When the black hole then evaporates via Hawking radiation, that radiation appears to be completely random, completely thermal, completely featureless. It carries no trace of what fell in. So when the black hole is finally gone, the information has vanished with it, not hidden somewhere, destroyed, erased from existence. This is not allowed, not in quantum mechanics, and yet it appears to be what happens. Hawking himself initially insisted that the information was destroyed, and that quantum mechanics would simply have to accept this exception. Many physicists spent decades arguing the opposite, that the information must somehow be encoded in the Hawking radiation in some subtle way we don't yet understand. Others suggested the information might be preserved in a remnant, some stable artifact that survives the evaporation. In 2016, Hawking and colleagues proposed that information might be stored in soft photons and gravitons, zero-energy particles, on the event horizon itself. None of these proposals have been proven. None of them have achieved consensus. The black hole information paradox, stated clearly in 1974, remains unsolved in the 21st century. Two theories, both proven, both tested to extraordinary precision, and they tell contradictory stories about something as fundamental as whether information, reality itself, can disappear. But there is one more place where these two pillars collide, and the collision produces what many physicists consider the worst prediction in the history of science. You'll remember from the previous chapter that the cosmological constant, the energy of empty space, is tuned to 1 part in 10 to the power of 120. The question we left open was, where does that number come from? Why is the vacuum energy so vanishingly small? And here is where things become genuinely surreal, because quantum field theory doesn't just fail to explain the cosmological constant, it actively, aggressively, spectacularly predicts the wrong value. In quantum field theory, empty space is not empty. It's seethes with quantum fluctuations, virtual particles constantly popping in and out of existence, borrowing energy from the vacuum and returning it on timescales so short they can never be directly observed. These fluctuations carry energy. The vacuum has energy. And when you calculate, using perfectly standard quantum field theory, how much energy the vacuum should have, you get a number that is 10 to the power of 120 times larger than what we observe. Let that land properly, not twice as large, not 1,000 times as large, 10 to the power of 120 times as large. Our best theory of matter and energy predicts that empty space should be so energetic that the universe would have torn itself apart in a fraction of a second after the Big Bang. Galaxies would never have formed, stars would never have ignited. You would not be here to contemplate this problem, and yet the vacuum energy is almost exactly zero. Something cancels it. Something reduces it by 120 orders of magnitude with extraordinary precision. We have no idea what. We have no mechanism. We have no principle. We have a number that should be enormous and an observation that it is tiny and nothing bridging the two. This is the vacuum energy catastrophe. It is not a metaphor. Physicists genuinely call it a catastrophe. The Nobel laureate Steven Weinberg described it as the most difficult problem in physics. It is not separate from the fine-tuning crisis we discussed before. It is the same crisis, viewed from the inside of quantum field theory. The universe's constants are not just unexplained. Our best physics actively makes the wrong prediction about the most important one, and then reality corrects our prediction by a factor that defies comprehension. And then there is the strangest problem of all, the one that physicists sometimes avoid discussing in public because it sounds too much like philosophy, and yet refuses to stay outside the room. Quantum mechanics describes the world in terms of wave functions, mathematical objects that encode the probabilities of all possible outcomes of a measurement. Before you measure a quantum system, it exists in a superposition of states. It is not in one place or another. It is, in some meaningful sense, in multiple states simultaneously. When you make a measurement, the wave function collapses to a single outcome. The act of observation selects a reality. This is strange enough for subatomic particles, but the interpretation becomes genuinely vertiginous when you scale it up to the entire universe. If quantum mechanics applies universally, and there is no principled reason to believe it doesn't, then the universe itself has a wave function. The entire cosmos, in all its complexity, exists as a quantum superposition of all possible histories, all possible configurations, and the wave function of the universe requires an observer to collapse it. But the universe existed for nearly 10 billion years before anything resembling an observer evolved. Before the first single-celled life, before the first nervous system, before the first brain capable of asking a question. If the wave function of the universe requires observation to collapse, who was observing it during those first 9 billion years? Who, or what, selected the reality we now inhabit from the infinite superposition of possibilities? The physicist John Wheeler spent decades arguing that the universe is, in some deep sense, participatory, that observers are not passive witnesses to a reality that exists independently of them, but are in some way constitutive of it. He spoke of a participatory universe, where the act of observation reaches backward in time through billions of years of cosmic history to give definite form to a past that was otherwise indeterminate. This is not mysticism. Wheeler was one of the most rigorous theoretical physicists of the 20th century, a man who coined the term black hole and worked with Einstein himself, and he concluded, after a lifetime of thought, that the relationship between observation and reality was not a footnote to quantum mechanics but its deepest secret. What does it mean that our universe's wave function required an observer? What does it mean that we are, in some sense, the mechanism by which the cosmos achieved definite form? These questions are not answered by any current theory. They are not even properly formulated yet. They exist in the silence between general relativity and quantum mechanics, in the gap that no known mathematics can bridge. Some physicists have refused to accept that silence as permanent. They have built radical frameworks, often at the margins of mainstream acceptance, to try to explain why the universe is the way it is rather than some other way. Roger Penrose, the mathematician who shared the 2020 Nobel Prize in Physics, has proposed what he calls conformal cyclic cosmology. In his framework, the Big Bang was not the absolute beginning. It was a transition, a boundary between one cosmic aeon and the next. Each universe begins in a Big Bang, evolves, expands, grows cold and empty as all its matter eventually decays and all its black holes evaporate, and then, in the infinite cold of maximum entropy, something remarkable happens. The geometry of a universe with no mass and no scale looks mathematically identical to the geometry of a Big Bang. The ending is conformally equivalent to a beginning. One universe's death becomes the next universe's birth. And Penrose has suggested that signals from the previous aeon might still be visible in our cosmic microwave background, faint circular patterns, ghost signals from the black hole collisions of a universe that preceded ours. The physicist Lee Smolin has proposed something even more Darwinian. He calls it cosmological natural selection. Every time a black hole forms, it gives birth, through a process we cannot yet describe, to a new universe inside it, with slightly mutated constants. Universes that produce more black holes leave more offspring. The constants of our universe are what they are because they have been selected across vast generations of universes for their capacity to produce the very structures, stars, supernovae, collapsed remnants that generate new universes. Fine-tuning in this framework is not a miracle. It is the result of a cosmic evolutionary process, playing out across scales and timescales that dwarf anything we can directly observe. Both frameworks are mathematically serious. Both are testable in principle, even if the tests are extraordinarily difficult. Both have largely been ignored by mainstream physics, not because they have been disproven, but because they require a conceptual leap that the field has not yet been willing to make. The dominant response to the fine-tuning problem, the vacuum energy catastrophe, and the incompatibility of our two greatest theories has been, for decades, to wait. To hope that a theory of quantum gravity, string theory, loop quantum gravity, something not yet imagined, will eventually arrive and dissolve the paradoxes. That theory has not arrived. What we are left with is a map of physics that works magnificently in two separate regions and catastrophically fails at their boundary. We are left with equations that produce infinities at the beginning of time and at the centers of black holes. We are left with information that quantum mechanics insists cannot be destroyed, and a physical process that appears to destroy it. We are left with a vacuum energy that is tuned to an impossible precision and a theoretical prediction that misses it by 10 to the power of 120. We are left with a universe that needed an observer and was, for most of its existence, unobserved. And here is the thought that some physicists have found themselves unable to dismiss, the thought that waits quietly at the edge of these accumulated silences. What if the problem is not that we haven't found the right equations yet? What if the problem is that we are thinking about reality in fundamentally the wrong terms? What if space, time, matter, and energy are not the foundational ingredients of the universe, but something more like the output, a surface appearance, an interface, a projection from something deeper that our current languages of physics don't even have words for? What if the universe, at its most fundamental level, is not made of things at all, but of something that looks far more like information? So we arrive at the edge of what physics can say. We have followed the cracks in the model, the impossible galaxies, the restless Hubble constant, the cosmological constant that refuses to behave, the fine-tuning that defies all probability, and finally the silence at the origin point where the equations collapse and the universe offers no explanation of itself. We have reached the place where the known tools give out, and yet the story does not end here, because some physicists, rather than retreating from the silence, have walked directly into it and come back with something extraordinary, not an answer exactly. Something stranger than an answer, a completely different question about what reality is made of. To understand where this leads, we need to begin not with galaxies or expansion rates, but with something that might seem entirely unrelated. We need to begin with a black hole, and with a question that almost nobody thought to ask. For most of the 20th century, black holes were understood as cosmic drains, objects so massive that nothing, not even light, could escape their gravitational pull. They were the ultimate destroyers of information. Whatever fell into a black hole was, by most accounts, simply gone, crushed beyond recovery. And because physicists had long assumed that the laws of thermodynamics, the laws governing heat, entropy, and the flow of information, were universal and inviolable, this created a quiet but serious problem. Entropy, in the thermodynamic sense, is a measure of disorder, of the number of possible states a system can occupy. The second law of thermodynamics says it always increases. But if information could simply vanish into a black hole, then entropy could effectively decrease from the perspective of the outside universe. Something was wrong. In the early 1970s, a young graduate student named Jacob Bekenstein decided to take this problem seriously. He proposed something that his supervisor, the great John Wheeler, initially found deeply uncomfortable, that black holes must have entropy. Not metaphorical entropy, real, measurable, thermodynamic entropy. And when Bekenstein calculated how much entropy a black hole should possess, the answer that emerged was astonishing in a way that nobody had anticipated. The entropy of a black hole was not proportional to its volume. It was proportional to its surface area, specifically to the area of the event horizon, that spherical boundary of no return surrounding the black hole's core. Think carefully about what this means. A black hole is a three-dimensional object. It has volume. If entropy were a property of its interior, of all the matter and energy compressed inside it, you would expect entropy to scale with that volume. More interior space, more possible states, more entropy. That is the intuitive expectation, but Bekenstein's calculation said otherwise. The entropy, all of it, was encoded on the two-dimensional surface wrapping the outside of the black hole. The interior, all that apparent depth and volume, was in some sense redundant. Everything physically meaningful about the black hole could be described by information written on its skin. Stephen Hawking was initially skeptical, but when he applied quantum mechanics to the problem, developing what became known as Hawking radiation, the discovery that black holes slowly emit thermal radiation due to quantum effects near the event horizon, he confirmed Bekenstein's result. The entropy of a black hole scales with surface area. This was not a curiosity, this was a law, precise and mathematically rigorous. And it planted a seed that would take another 2 decades to fully germinate. If a black hole's three-dimensional information content can be completely encoded on a two-dimensional surface, what does that imply about the nature of three-dimensional space itself? The physicist Gerard Hooft, who would later win the Nobel Prize, began to think through the implications in the early 1990s. He suggested that the principle might be general, that in any region of space, the maximum amount of information that region can contain is not determined by its volume, but by its surface area. Leonard Susskind developed this idea further and gave it a name, the holographic principle. The name itself is deliberate and evocative. A hologram is a two-dimensional object, a flat photographic plate that encodes a three-dimensional image. When you illuminate it correctly, a full three-dimensional scene appears to emerge from it. The holographic principle proposes something analogous about the universe itself, that our three-dimensional reality, with all its apparent depth, all its volume, all its spatial richness, might be the emergent projection of information encoded on a two-dimensional surface at the boundary of the cosmos. This was a radical philosophical provocation, but it remained somewhat abstract, a suggestive idea without a rigorous mathematical scaffolding until 1997. That year, a young Argentine physicist named Juan Maldacena published a paper that transformed the holographic principle from philosophical speculation into mathematical fact, at least within a specific theoretical framework. The paper is now the most cited piece of scientific literature in the history of physics. Its implications have not stopped reverberating. What Maldacena demonstrated is known as the ADS/CFT correspondence. The abbreviations are dense, but the idea is precise. ADS stands for anti-de Sitter space, a particular type of universe with a specific geometric structure, slightly different from the flat or positively curved space of our own cosmos. CFT stands for conformal field theory, a type of quantum field theory, the mathematical language physicists use to describe particles and forces without gravity operating on the boundary of that space. What Maldacena showed is that these two descriptions are not merely analogous, they are mathematically equivalent. Every physical event that occurs inside the ADS space, every particle interaction, every gravitational phenomenon, every quantum process, can be described with perfect completeness by the quantum field theory living on the lower dimensional boundary. Nothing is lost, nothing is missing. The full three-dimensional gravitational universe is dual to the two-dimensional boundary theory. They are two different languages describing the same reality. This is not a metaphor. This is not a useful approximation. The correspondence is exact, and what it means, philosophically, is devastating in the most productive possible sense. It means that gravity, the force that curves space-time, that holds galaxies together, that defines the large-scale structure of the cosmos is not necessarily fundamental. It can be derived. It can be reconstructed from quantum information on a surface that does not itself contain gravity. Gravity, in other words, might be emergent. Space itself might be emergent. The three dimensions we move through every day might be a kind of collective illusion, not in the dismissive sense of being unreal, but in the precise sense of being derived from something more fundamental that operates at a different level of description. A Dutch physicist named Erik Verlinde took this implication and ran with it in a direction that shook the physics community when he published his proposal in 2010. Verlinde argued that if gravity is emergent, if it arises from underlying information dynamics rather than being a fundamental force written into the fabric of spacetime, then we need to completely rethink what gravity is. His framework, called entropic gravity, proposes that what we experience as gravitational attraction is actually a thermodynamic effect. It is what happens when information encoded on holographic surfaces, imaginary boundaries surrounding regions of space, tends toward higher entropy configurations. Objects move in gravitational fields, not because spacetime is curved by mass in the way Einstein described, but because moving in that direction increases entropy. Gravity, on this view, is as fundamental as temperature. Temperature is real. You can measure it, it has effects, but it is not a basic ingredient of physics. It emerges from the collective behavior of vast numbers of particles. Verlinde says gravity is the same kind of thing. The implications for cosmology are immediate and startling. If gravity is emergent from holographic information, then dark matter, that invisible, undetected substance that cosmologists have invoked for decades to explain the way galaxies rotate and the way large-scale structure forms, might not exist as a particle at all. The anomalous gravitational effects we attribute to dark matter might simply be what emergent gravity looks like in regions where matter is distributed in ways that cause deviations from what Newton or Einstein predict. Verlinde's equations, when applied to galactic rotation curves, produce results that match observations without requiring a single dark matter particle. Not perfectly, not in every case, and the framework is genuinely contested. Many physicists remain skeptical, and the theory is not yet complete, but the match is striking enough that it cannot be dismissed. And if dark matter dissolves as a concept, then dark energy, the other great invisible pillar of the Lambda CDM model, faces similar scrutiny. If the accelerating expansion of the universe is also an emergent thermodynamic effect of information on cosmic-scale holographic boundaries, then the cosmological constant, with its catastrophic fine-tuning problem, its factor of 10 to the power of 120 discrepancy, might be a symptom of using the wrong ontology. Not a true constant of nature, an artifact of trying to describe an emergent phenomenon using the wrong fundamental language. Now return to the James Webb Space Telescope. Return to those galaxies that should not exist, massive, structured, star-dense, appearing in the universe's first few 100 million years, when the Lambda CDM model says they had no time to form. And return to the Hubble tension, that stubborn, worsening disagreement between the expansion rate inferred from the cosmic microwave background and the rate measured directly from nearby cosmic objects. We have been treating these as anomalies within the existing framework, cracks in an otherwise sound model, but the holographic perspective invites a more radical interpretation. What if they are not anomalies within the model? What if they are symptoms of the model itself being written in the wrong language? Consider the cosmic microwave background, that ancient light released 380,000 years after the Big Bang, which we use to measure one value of the Hubble constant. The patterns in that radiation, the temperature fluctuations across the sky, are treated by Lambda CDM as a snapshot of initial conditions, fluctuations in matter density that gravity then amplified into galaxies over billions of years. But this analysis assumes a specific relationship between information, volume, and entropy that is entirely classical and three-dimensional. If the holographic principle is correct, if the early universe encoded its information on a boundary in a fundamentally different geometry than we assume, then the entire decoding of that microwave background might be systematically wrong. Not wrong in its measurements, wrong in its translation. We might be reading a two-dimensional text as if it were three-dimensional, and then wondering why the map does not match the territory. The Webb anomalies compound this. The early universe, in the holographic picture, is a regime where the emergent nature of spacetime is least settled, where the transition from boundary information to three-dimensional volume is most incomplete or most different from its current form. If spacetime itself was still, in some sense, crystallizing in those first hundreds of millions of years, if the dimensions we take for granted were still resolving from an underlying information substrate, then the concept of distance, of look-back time, of what it means for a galaxy to be located at redshift 8 or 10 or 12, might not map cleanly onto our current three-dimensional intuitions. The universe in its infancy might have been, in a precise technical sense, differently shaped in its information geometry than it is today, and galaxies that appear impossibly large and structured for their look-back time might simply be places where that information geometry allowed rapid organization that classical three-dimensional physics cannot accommodate. This is not hand-waving. Theoretical work connecting the holographic principle to cosmological initial conditions is active, serious, and mathematically detailed. Physicists including Nima Arkani-Hamed, whose work on the amplituhedron has suggested that spacetime and locality may themselves be emergent from more primitive mathematical structures, have pursued frameworks in which the universe's history is better understood as an unfolding of information from a boundary than as a sequence of events in a pre-existing spacetime volume. The Hubble tension, in this light, becomes interpretable as a consequence of trying to apply a single fixed expansion rate to a universe whose geometry has been evolving in ways that classical cosmology does not capture. Because classical cosmology takes the three-dimensional stage for granted, while the holographic view says the stage is itself part of the performance. There is a more personal and disorienting dimension to all of this that deserves to be named directly. The holographic principle, if correct, does not merely revise our cosmological models, it revises what we mean by the word real. When we say something is real, we typically mean it exists in space. It has a location, a volume, a presence. The chair you sit in is real because it occupies three-dimensional space in a way that resists other objects. But if three-dimensional space is emergent, if depth and volume and the sensation of moving through a spatial world are derived properties of information encoded on a boundary we cannot see or directly access, then reality is something other than what it appears to be. Not less real, not illusory in the way the word illusion implies diminishment, but differently structured, more abstract in its foundations than our senses lead us to believe. This is, of course, not the first time that the deep structure of reality has turned out to be radically unlike its appearance. Solid matter turned out to be mostly empty space held in structure by electromagnetic forces. Time turned out to run at different rates depending on velocity and gravitational field. Particles turned out not to have definite positions or velocities until the moment of measurement. Each of these revelations required surrendering a prior intuition that felt self-evident. The holographic principle may be the deepest of these surrenders, the one in which space itself, the container of all experience, is revealed to be a derived description rather than a foundation. And here is where the silence we encountered in the previous chapter begins to speak again, but in a different register. When general relativity's equations collapse at the Big Bang singularity, they do so because they are equations of geometry, equations that describe the shape of three-dimensional space over time. If three-dimensional space is emergent, then asking those equations to describe the moment before space had fully emerged is asking them to operate outside their domain. The singularity is not necessarily a physical catastrophe. It might be a translation error. A moment where the three-dimensional language we use to describe reality simply does not yet apply, because reality at that juncture was still being written in a different code. The reconciliation of general relativity and quantum mechanics, that unfinished business that physics has carried for a century, might lie precisely here. In the holographic correspondence, quantum mechanics lives on the boundary. Gravity emerges from it in the interior. They are not in conflict because they are not at the same level of description. Quantum mechanics is the more fundamental language. Gravity is what it looks like when you read that language in 3 dimensions. The two pillars that seemed irreconcilably incompatible might turn out to be the same pillar seen from different angles, and the angle we have been standing at for all of human history has been inside the projection, mistaking the image for the source. Whether this is correct is not yet known. Maldaceno's result holds for anti-de Sitter space, which is not quite the geometry of our universe. Extending it cleanly to our cosmos remains an open and fiercely worked mathematical problem. Verlinder's entropic gravity is promising but incomplete. The holographic cosmology program is ambitious and contested. The community is divided, the calculations are hard, and the experimental confirmations are indirect at best. But the principle has survived every test applied within its domain, and it has given physicists something precious in the landscape of broken models, not just a patch for the cracks, but a completely different blueprint. One that suggests the universe's deepest mysteries are not going to yield to louder telescopes or more powerful colliders alone, but to a reconception of what we are actually looking at when we look at anything at all. Which brings us finally to the question of what comes next. If the universe is information, if gravity is emergent, if space is the output rather than the input, if the Big Bang is a translation problem rather than an absolute beginning, then physics is not merely incomplete, it is being rebuilt from the inside out. And somewhere in that reconstruction, there may be answers not only to the Hubble tension and Webb's impossible galaxies, but to the question that has haunted everything we have covered in this exploration, not just what the universe contains, but what it is. And whether, on the other side of all these broken models, there is a picture of reality that we are only just beginning to have the mathematics to see. So here we stand, at the edge of everything we thought we knew. The holographic principle didn't arrive as a gentle revision. It arrived as a detonation. The idea that three-dimensional reality might be encoded on a two-dimensional boundary, that the volume of space you move through every day could be, in some profound sense, a projection, is not the kind of idea that leaves your understanding of the universe intact. And yet, as radical as it sounds, it followed logically, almost inevitably, from the mathematics of black holes, from entropy, from the deep structure of quantum field theory. Gerard Hooft didn't dream it up on a whim. He was chasing an inconsistency, following the thread, and the thread led somewhere no one expected. But here is the question that holography leaves hanging in the air, the question this entire journey has been building toward. If reality is informational at its foundation, if space itself may be emergent rather than fundamental, then what does that mean for all the models we've built on top of it? What happens to Lambda CDM, to the cosmological constant, to cold dark matter, to every elegant equation we've used to describe the cosmos, when the floor beneath them turns out to be something stranger than anyone imagined? What comes after broken physics? That is the question we have to face now. Not with despair, with the particular kind of exhilaration that has always preceded the greatest leaps in human understanding. Let's begin with what the data is actually telling us, because the data at this point is not subtle. The James Webb Space Telescope found galaxies that were too massive, too structured, too chemically mature to exist within the timeline Lambda CDM prescribed. The Hubble Tension, that stubborn, maddening disagreement between two independent methods of measuring cosmic expansion, has only sharpened with time, surviving every attempt to explain it away as measurement error. The dark energy spectroscopic instrument, surveying the universe's three-dimensional structure across billions of years, released results in 2024 suggesting that dark energy may not be constant at all, that it has evolved, weakened perhaps, over cosmic time. The cosmological constant isn't behaving like a constant. Fine-tuning sits unexplained at 1 part in 10 to the power of 120. And the two great theoretical pillars of physics, general relativity and quantum mechanics, still refuse to speak the same language. This is not one crack in the edifice. This is the edifice itself asking to be rebuilt, so physicists have been building. Quietly, competitively, sometimes controversially, a collection of successor frameworks has been taking shape, each one attempting to absorb the anomalies that Lambda CDM cannot. None of them has won, but each of them illuminates something real. The first family of alternatives doesn't touch dark energy at all. Instead, it asks whether we've been thinking about gravity itself incorrectly. Modified gravity theories, most famously MOND, modified Newtonian dynamics, developed by Mordechai Milgram in the early 1980s, and its relativistic extension MOG, modified gravity, propose that at extremely low accelerations, the kind experienced by stars in the outer arms of galaxies, gravity doesn't behave quite as Newton or Einstein described. Rather than invoking invisible dark matter to explain why galaxies rotate the way they do, these theories say the law of gravity itself has a different shape at those scales. MOND has been remarkably successful at predicting galaxy rotation curves, sometimes eerily so, reproducing observations that dark matter models struggle with. But it has also failed badly in other contexts: galaxy clusters, the cosmic microwave background, large-scale structure. Webb's data, showing those massive early galaxies, doesn't obviously favor MONDs either, because the problem there is one of cosmic timeline, not rotation. Modified gravity theories explain some anomalies and stumble on others. They remain serious scientific proposals, not fringe ideas, but they are partial solutions at best. Then there are the early dark energy models. These approaches accept the existence of dark energy, but argue that it wasn't always the quiet, steady background hum described by the cosmological constant. Perhaps, in the very early universe, before and around the time of recombination, when the cosmic microwave background was released, dark energy had a different, stronger character. A brief pulse of additional energy density in the early universe would change the sound horizon, the characteristic scale imprinted in the cosmic microwave background, and that change could, in principle, reconcile the two conflicting Hubble constant measurements. Early dark energy has attracted serious mathematical development and serious criticism in roughly equal measure. The tension it resolves in one place tends to create new tensions elsewhere, in the clustering of matter, in the growth of large-scale structure. Webb's impossibly early galaxies actually create additional pressure here. If early dark energy accelerated expansion in the infant universe, it might have affected how quickly structure could form, which is precisely what those early massive galaxies are challenging. The models are being revised in real time, constrained from multiple directions simultaneously. More exotic still are the interacting dark sector scenarios. These models propose that dark matter and dark energy are not independent substances sealed off from each other, but that they interact, that there is some exchange, some coupling between the invisible components that together constitute roughly 95% of everything in the universe. Interacting dark sector models can, depending on the specifics, relieve the Hubble tension and alter the growth of structure in ways that might accommodate Webb's early galaxies. The DESI results, suggesting dark energy that evolves, actually provide some tentative encouragement for these scenarios, because a truly constant vacuum energy wouldn't interact with anything. If dark energy is dynamical, if it changes over time, interaction becomes at least conceptually easier to motivate. But these models carry enormous theoretical freedom, which is both their strength and their weakness. A framework with enough free parameters can fit many things. The challenge is prediction, making sharp, testable claims that distinguish the interacting dark sector from its competitors. And then there are the quantum gravity approaches, string theory, loop quantum gravity, causal set theory, and their various relatives. These are not primarily cosmological models. They are attempts to unify general relativity and quantum mechanics at the deepest level, but their implications for cosmology are profound. String theory, in particular, has generated the concept of the string theory landscape, an almost inconceivably vast collection of possible universes, each with different values of the fundamental constants, the cosmological constant among them. In this picture, our universe's fine-tuned constants aren't miraculous coincidences. They are the result of a cosmic lottery in which only universes compatible with observers can be observed. This is the anthropic argument taken to its logical extreme, and it remains deeply controversial precisely because it is so difficult to falsify. Loop quantum gravity offers a different path, proposing that space and time themselves are quantized, made of discrete finite units rather than continuous fabric, which naturally avoids the singularity at the Big Bang and replaces it with a bounce, a prior contracting universe that reached a minimum size and expanded outward. Some versions of loop quantum cosmology make predictions for the cosmic microwave background that could, in principle, be tested. Webb data doesn't directly adjudicate between these quantum gravity approaches, but it applies pressure. Any framework claiming to describe the universe's origin must account for what we actually see in the early universe, and what we see keeps defying expectation. Here is the honest summary. No single successor framework has absorbed all the anomalies. The data from Webb, from DCE, from increasingly precise measurements of the cosmic microwave background, it constrains, it pressures, it disfavors certain specific implementations of each model, but it has not yet decisively crowned a successor. We are in the phase that always precedes a paradigm shift, the phase of productive chaos, where the old model is clearly broken and the new one hasn't yet crystallized. And this is, historically, exactly where the most important scientific revolutions have lived. At the turn of the 20th century, classical physics faced its own accumulation of impossible anomalies. The ultraviolet catastrophe, the prediction by classical theory that a heated object should radiate infinite energy at short wavelengths, which obviously no heated object does, sat there, unresolved, embarrassing, suggesting something was fundamentally wrong with how physicists understood energy. The precession of Mercury's orbit around the Sun didn't match Newtonian predictions by a tiny but stubbornly persistent margin that decades of refinement couldn't explain. The Michelson-Morley experiment found no evidence for the luminiferous ether, the medium through which light was supposed to travel, leaving physicists with no explanation for how light could be a wave without a medium to wave through. Individually, each anomaly might have been a measurement error or an overlooked factor. Together, they were something else. They were the universe insisting it had been misunderstood at a foundational level. Max Planck's quantum hypothesis resolved the ultraviolet catastrophe. Einstein's special and general relativity resolved Mercury and the ether. Within 15 years, the entire conceptual foundation of physics had been rebuilt. Not because the old physics was useless, classical mechanics still lands spacecraft on the moon, but because it had been revealed as a local approximation exquisitely accurate within a certain range of scales and speeds and wrong outside that range. Lambda CDM is in that position now, and that phrase, local approximation, deserves to be examined carefully because it is the most precise description of what we are learning. Lambda CDM works. It works beautifully for the nearby universe, for the late-time universe, for scales and epochs that don't push the model to its limits. It predicts the acoustic oscillations in the cosmic microwave background with extraordinary precision. It correctly describes the large-scale distribution of galaxies across hundreds of millions of light-years. It is one of the most successful quantitative frameworks in the history of science. But, and this is the pattern that has now emerged unmistakably, the further back in time we probe, the earlier the epoch, the larger the scale, the more the model struggles. The early massive galaxies Webb discovered live 12 to 13 billion years in the past, near the model's outer boundary of validity. The Hubble tension emerges precisely from comparing measurements anchored in the early universe to measurements anchored in the late universe. The DESI anomaly appears when surveying the universe's evolution across cosmic time. The model's failures cluster at its edges, at the extremes of time and scale, exactly as you would expect from a local approximation being extended beyond its domain of validity. It is, in the most literal sense, like using a flat Earth model to navigate a continent. Within a city, within a region, the flatness assumption works perfectly well. The curvature of the Earth is negligible. Extend the map to planetary scales, and the errors accumulate into catastrophe. We have been navigating the cosmos with an extraordinarily sophisticated flat Earth model, and the James Webb Space Telescope has, for the first time, given us photographs from the curvature. Now, here is where the conversation becomes genuinely uncomfortable, because some of the physicists thinking hardest about these questions have begun to take seriously a possibility that, a decade ago, would have been confined to philosophy seminars and science fiction. The holographic principle established that reality may be informational at its base. The fine-tuning crisis established that the constants permitting our existence appear calibrated with impossible precision. The failure of physics at the singularity established that the universe's origin lies beyond the reach of any current theory. These facts, taken together, have nudged some of the most serious scientific minds toward a question they are reluctant to ask but cannot stop asking. What if the universe is, in some meaningful sense, computational? Max Tegmark, the MIT cosmologist, has developed what he calls the mathematical universe hypothesis. The proposal that mathematical existence and physical existence are the same thing, that every mathematically consistent structure exists physically somewhere, and that our universe is simply one such structure being instantiated. This is not a mystical claim. It follows from taking mathematics seriously as something discovered rather than invented, and from asking what would distinguish a mathematical universe from a physical one if they are, at their foundation, indistinguishable. Konrad Zuse, the German computing pioneer, proposed in 1969 that the universe might be running on a discrete computational substrate, a cosmic calculation of which physical reality is the output. John Wheeler, one of the most celebrated physicists of the 20th century, spent his later career developing what he called it from bit, the idea that every physical thing, every particle, every field, every dimension of space derives its existence from information, from binary choices, from the universe answering questions about itself. These are not the ravings of people who have abandoned rigor, and several Nobel laureates have stated, with varying degrees of comfort, that the simulation interpretation of reality, the idea that our universe exists within some form of computation or mathematical structure external to itself, cannot currently be ruled out. Not confirmed, not endorsed, but not ruled out. That is a statement worth sitting with. When the question of whether our universe is simulated has moved from science fiction to something that serious physicists say cannot be formally excluded, something has changed in the conversation humanity is having with itself about the nature of existence. Webb's anomalies didn't create this conversation, but they accelerated it. Every galaxy that should not exist, every measurement that contradicts the model, every constant fine-tuned beyond all probability, each one quietly erodes the comfortable certainty that Lambda CDM was describing reality as it fundamentally is, rather than reality as it locally appears. And this brings us finally to what this means for us, for human beings. For the species that named the stars and mapped the microwave background and built a telescope so sensitive it can detect the light of galaxies that formed when the universe was barely 300 million years old. There is a particular kind of vertigo that comes with scientific revolution. It happened when Copernicus displaced the Earth from the center of the cosmos. It happened when Darwin placed humanity within the continuity of life rather than above it. It happened when quantum mechanics revealed that the solid, deterministic world of everyday experience is built on a foundation of irreducible uncertainty. Each time, the first response was resistance, not because scientists are cowardly, but because the implications were enormous. To accept the revolution was to accept that the story you'd been telling yourself about where you live and what you are had been a local story, a partial story, true in its domain and incomplete beyond it. We are at that threshold again. The universe we thought we inhabited, a cosmos 13.8 billion years old, governed by general relativity on large scales and quantum mechanics on small scales, filled with ordinary matter, dark matter, and a gently accelerating dark energy described by a constant vacuum energy, that universe is becoming a local story. It describes our corner of space and our slice of cosmic time with remarkable fidelity. But the evidence accumulating from Webb, from DESI, from decades of theoretical struggle, suggests that beyond that local story there is something stranger, something deeper, something our current language of physics cannot yet fully speak. This is not failure. This is the opposite of failure. Science is the only human endeavor that makes progress by discovering how wrong it has been. Every model that breaks open at its edges, every constant that misbehaves, every galaxy that appears where it shouldn't, these are not signs that science has reached its limits. They are invitations. They are the universe, larger and stranger than we imagined, leaning down toward the small, improbable creatures who built telescopes and asked questions, and whispering, "You have been looking at the map, now look at the territory." We don't know yet what lies on the other side of broken physics. We don't know which of the successor frameworks will absorb the anomalies, or whether the right framework has even been proposed yet, or whether the revolution ahead will be as complete and disorienting as the ones that gave us relativity and quantum mechanics. We don't know whether the universe is holographic in the full sense, or computational, or something that doesn't yet have a name. But we know this, the fact that we can ask these questions, that we built Webb, that we can hear the universe contradicting itself across 13 billion years of light, that is not a small thing. A Nobel Prize winner looked at the data and said, "This isn't our universe." And perhaps that's exactly right. Perhaps the universe we thought we knew was always too small. Perhaps the one we are beginning to glimpse is vast enough to deserve the name. The questions are open, the instruments are running, the light is still arriving. We began with a photograph. Thousands of galaxies, ancient and impossible, hanging in the dark like an accusation. And everything we thought we understood about the universe began, quietly, to come apart. The galaxies were too old, the expansion rate wouldn't hold still, the cosmological constant turned out to be neither constant nor explained. The fine-tuning required to produce a universe capable of asking questions about itself defied every honest attempt at probability, and when we reached back to the very first moment, to the singularity where everything began, physics fell silent. Not because we lacked the instruments, because we had finally found the edge of what physics is allowed to know. But here is what stays with you, long after the equations and the anomalies and the Nobel laureates have faded from memory. The universe is not behaving like a brute, indifferent machine that happened to fall together. It is behaving like something that is hiding something. Every layer we peel back reveals not clarity but deeper structure. Not answers, but more precisely calibrated questions. The closer we look, the more it appears that reality is not made of matter. It is made of meaning encoded on surfaces we cannot directly see, in a language we have barely begun to learn. We do not know if the universe is a simulation or a hologram or something so strange that we lack the concepts to name it. We only know that the map we drew is wrong and the territory is far larger and far stranger than we imagined. Perhaps the most unsettling discovery James Webb actually made has nothing to do with any galaxy. It is this, that we are conscious pieces of a universe that cannot fully explain itself, staring outward into the dark, and finding, staring back, a mystery that looks almost deliberate.